students, all of you, welcome to the session BYJU'S exam preparation. Welcome to BYJU'S exam preparation, the most comprehensive preparation for all exams. Yes, students, all of you, welcome to the session. I'm starting a new series on electrical machines. We'll see some important models of questions based on the transformers who are preparing for GATE and ESE 2022. Whatever the models of questions that I'm going to give with respect to transformers. I divided the transformer concepts into different concepts that I divided based on each topic, concept wise, topic wise, that I am going to solving the questions today. I already done the series on induction missions, DC missions and synchronous missions. Now I am starting a series on transformer students. This very important topic who are preparing for GATE and ESE. Very important students. Today topic is based on the transformers, construction and principle of transfer. I am going to explaining today construction and principle, tomorrow EMF equation. Next continuation, I am solving the questions based on the operation of transformer, equivalent circuit of transformer, losses and testings of transformer, yes friends, efficiency of transformer, regulation of transformer, auto transformer, three-phase transformer, parallel operation of transformer. Like that, I divided into different topics. Based on each topic, I am solving the different models of question students who are preparing for GATE and ESE. It is most important models of question students. Yes. Vandana Sandy, good evening. Welcome to the session. All of you, welcome to the session students. Yes friends, before starting the today topic questions, first let me introduce myself. Students, my name is Surendra Babu. For 10 years, I am educating the students for GATE, ESE and PSUs in electrical and electronics engineering. I mentored more than 15,000 plus students. These are the subjects I am teaching for various competitive point of view: network theory, power electronics, electrical machines, power systems, electrical and electronic measurements, control systems, transducers and mechanical instrumentation. Friend, this is my Telegram channel. Who are not joined still now, you please join this channel for more updates about my lectures. And if you have any doubts, clarification, you please share your doubts in the channel. Please join the channel using this link, students. Yes. Yes, students, all of you, welcome to the session. Devika, good evening. All of you, welcome to the session, students. The first question is displaying on the screen. Come on, students, check your knowledge solving of these questions. This is a fundamental question already framed in GATE exam and ESE exam also. It is a fundamental question. The laws of electromagnetic induction are summarized in the following equation. The laws of electromagnetic induction is summarized in the following equation. Come on, students. Yes, what is the answer? It is asked for what is the laws of electromagnetic induction, but it is given that combination of Faraday's law and Lenz's law. It is asked for Faraday's law and Lenz's law, students. We know that according to Faraday's law, actually, you know one formula. Yes, friends, E equal to induced EMF equal to N into d pi by dt. This is Faraday's second law. According to Faraday's second law. It's a Faraday's second law, students. Yes, friends, come on. But that means Faraday's second law will give the magnitude of statically induced EMF. It gives the magnitude of statically induced EMF. Very good. Devika, Spandana, yes. Naveen Kumar, very good. It gives the magnitude of statically induced. But according to Faraday's and Lenz's law, but you want to consider the Lenz's law also. Why? Because direction is also considered. Because it is given Lenz's law. The Lenz's law gives the direction of statically induced. This gives Faraday's plus Lenz. Yes, students. This gives the combination of Faraday's plus Lenz law. Yes. Now tell the students. This is E equal to minus dn pi by dt. N pi is nothing but a flux linkage. N pi is nothing but a flux linkage. That is minus d psi by dt. Then which option is correct, students? Option C is correct. Very good. Very good, students. Very good. Shudhir, yes, option C is correct. Very good. One more question, students. Come on. Please concentrate on the concept. Please concentrate on the concept, students. Yes, you can get the concept by solving the questions also. That is the concept through questions. Two transformers of the same type using the same grade of iron and conductor materials are designed to work at the same flux and current densities. But the linear dimensions of one are two times those of the other in all respects. It is given that linear dimensions. The ratio of kVA of the two transformers is closely equals to dash. Yes, students, come on. How to answer this question? It is very simple. Please concentrate. But the solution for this problem. We know the students, kVA is proportional to E into I. kVA rating of transformer equal to product of voltage and current. Then kVA 2 by kVA 1. I'm doing kVA 2 by kVA 1 equal to, yes students, E2 by E1. Yes, come on students. This E2 by E1 into I2 by I1. E2 by E1 into I2 by I1. Yes. But what it is given here? The flux density is constant and the current density is also constant. Same flux and current densities. We know this EMF equation, students. E equal to 4.44 Bm AN N1. Once we can, yes, 4.44 F into Bm AN N1, students. F into Bm AN N1. Yes, F into Bm AN N1. Given that it is a constant, flux density is constant. Yes, friends, the frequency is also constant. Yes, number of turns is also constant. But we are changing the linear dimensions. Once we are changing the linear dimensions, area will be changes. That is, E is proportional to AN2. AN. E is proportional to AN, students. Yes, come on, students. Because linear dimensions are changed means area is changed. That's why area is variable here. Shall you write like this? E2 by E1 equal to AN2 by AN1. Now tell the students, linear dimensions are double. That means you take the length and width is double. If the length and width is double, then what about the area, students? Area becomes 4 times. Let's assume that I'm increasing the linear dimensions of the, I'm making the increasing the linear dimensions of the transformer 2. That's why I'm taking this is 4A and 1. If the dimensions are doubled means area becomes 4 times. This is cancelled. Then what is E2 by E1 you can get, students? Come on. What is the E2 by E1 you can get? This E2 by E1 you can get. If it is not visible here, if it is not visible, in the next slide I will write. Yes, students. Come on. Then what the E2 by E1, students? This E2 by E1 equal to, this is 4 times of AN1 by AN1. Sir, why you taken 4 times, sir? Because linear dimensions are double, area becomes 4 times. Yeah, this is. Next, one more condition is given. Current density is constant. We know that J equal to I by A. This condition also given, students. Current density is constant. If the current density is constant means I is proportional to A. Then shall you write like this? I2 by I1 equal to, that is AN2 by AN1. This is linear dimensions are double means area becomes 4 times. This is also 4. Now, what are the kVA 2 by kVA 1? What are the formula given, students? kVA 2 by kVA 1 equal to, come on students, E2 by E1 into I2 by I1. What is E2 by E1? You got 4. What the I2 by I1 also 4. That's why if linear dimensions are double, kVA of one transformer is 16 times of kVA of another transformer. Then which option is correct, students? Come on, students. Which option is correct? This is option A is correct. Which is correct? Option A is correct. Yes, friends. The actual meaning of linear dimensions. Yes. Linear dimensions means length and breadth. You take the length and breadth. And length 2 times, breadth is also 2 times, then it becomes 4 times. Area becomes 4 times. Yes, very good, Sudhir. Yeah, that is correct. Very good. Understand, Sandy? Linear dimensions means you take the length and breadth. That is double. Length is double, breadth is double, means area becomes 4 times. Yes, students. Come on. One more question is displaying on the screen, students. Let me check how many number of students can respond. Come on, students. The single phase 50 Hz iron core transformer results in the circuit has both vertical arms of cross sectional area is 20 centimeter square and both the horizontal arms of cross sectional area is 10 centimeter square. If the windings are shown were wound on opposite horizontal arms, the mutual inductance will be. Actually, initially these windings are placed in the vertical arms. If these are wounded on the horizontal arms, what is the mutual inductance, students? That is the question is asked. Then in this case, if it is placed, then what is the mutual inductance? Come on, students. Then it becomes double, it becomes remains same, B halved becomes 1/4. Can anybody? Yes, students. The single phase 50 Hz iron core transformer. Then I want to write, because area is given, I want to write the relation between the mutual inductance and area. Students, what is the solution for this problem? It is very simple. Come on, students. Yes. How to answer this question? Yes, come on. Can anybody answer? Yes, most of the students they given option C. It is B halved. Very good. Very good. That is correct, students. Very good. Yes. We know this one. L equal to N square mu A by L. Mu A by L. That is L is proportional to area. That means then what is M? M is also. Yes, students. M is proportional to. Yes, come on, students. M is proportional to A. Then M2 by M1 equal to A2 by A1. A2 by A1. Now we are placing on the horizontal. Then M2 equal to, this is 10 by 20 into M1. This is M1 by 2, students. Then area becomes this mutual inductance becomes halved. It becomes halved. Then which option is correct, students? It becomes halved. Very good. This is option C is correct. Very good, sir. Come on, students. One more question. Yes, come on. The transformer is excited with square wave current source. Then the shape of the induced EMF will be. The transformer is excited with square wave current source. What is the shape of the induced EMF? Can anybody answer? The transformer is excited with square wave current source. Then the shape of the induced EMF, students. Yes. We know that E equal to L into di by dt. L into di by dt. Then L into, yes, students, d by dt of square wave. Yes, L into d by dt of square wave. The current is square wave. Square wave, differentiation of square wave. Square wave is nothing but a step. Differentiation of step is nothing but a impulse. We can get the impulse, students. That is, the induced EMF is the impulse. Then it is not the answer, it is not the answer. But given is current induced EMF. We know in transformer, students, this is the magnetizing current. This is the magnetizing current. This is the supply voltage. You know this one, and this is E1. The fundamental vector diagram that you know, E1, E2. That is induced EMF. EMF lags I mu. EMF lags I mu. Angle of 90 degrees. Angle of 90 degrees. Angle of 90 degrees, students. That's the reason why it is an impulse wave with 90 degree displacement. Very good, students. It's option C. Very good, Naveen Kumar. Yes, Spandana, it is option C. It is an impulse wave with a 90-degree displacement. 90-degree displacement. I think all of you know this one. Differentiation of square wave, we can get the impulse wave. Here I am giving some notes, students. I think all of you well known this one. You already studied even in signals and systems, even in control systems also. This is very important. Yes, friends. Different integration of step. Integration of step is nothing but a which one, students? Integration of step is nothing but a ramp, or integration of step is nothing but a square. It is nothing but a square. Integration of square is nothing but a which one, students? Square. That is, you take the triangular waveform. Step or square waveform. Ramp or triangular. Yes, friends. Integration of ramp. Integration of ramp is which one, students? Parabola. Integration of ramp is nothing but a parabola. Yes, come on, students. Integration of ramp is nothing but a parabola. This integration of step. Yes. Integration of impulse, or if you take the differentiation. Differentiation of step. Differentiation of step. Which one, students? Impulse. Impulse. This differentiation of, or it may be you can take square. It may be step, or you can take in the form of square also. A positive step and negative step becomes a one square waveform. D by dt of square. It becomes which one, students? Impulse. This minimum knowledge is required. Then differentiation of ramp. Differentiation of ramp. Which one, students? Step. Differentiation of parabola. Differentiation of parabola. Which one, students? Ramp. Here also you can write differentiation of ramp means triangular. Differentiation of triangular waveform. The differentiation of triangular waveform is square waveform. Square wave. Like this we can take, students. Here also integration of impulse. Integration of impulse is nothing but a step. This minimum knowledge is required during solving of these models of problems, students. These models of problems. And one more point to remember, students, one more note. Simply remember one statement. If it is voltage excitation, if it is voltage excitation, if it is voltage excitation, come on, students, if it is voltage excitation, input waveform and output waveform is same. Input waveform and output waveform is same. If current excitation is given, transformer, if current excitation, students, if it is current excitation, if it is a current excitation, students, output equal to, yes, students, differentiation of input. Output equal to differentiation of input. That you remember. If it is a voltage excitation, input and output waveforms are same. Again, no need to check. If current excitation is given, output equal to differentiation of input. Okay, here in this question, which excitation is given, students? In this question, which excitation is given? Transformer is excited with square wave current. Current excitation is given. That's why output is nothing but a differentiation of input waveform. Clear, students? Yeah. One more question is displaying. Yes, come on, students. The transformer is excited with square wave voltage source. Then shape of the induced EMF. It's very simple. It's very simple, students. Transformer is excited with square wave voltage source. Voltage source excitation. Then input and output waveforms are same. It is excited with square wave. Square wave. That means output is also square wave. Output is also square wave. Option C and option D is wrong. Yes, friends. Because it is which excitation? Voltage excitation. If voltage excitation is given, input and output waveforms are same. Now, voltage excitation. We know this one. This is the voltage, students. Just now I given this vector diagram. And this is the I mu. This is the I mu. And this is the E, induced EMF. E1 or E2. Then what the angle between these two is how much, students? That is 180 degrees. That is EMF lags. EMF lags. V. By angle of how much, students? 180 degrees. That's why which option is correct? A square wave with 180 degree displacement. Not 90 degrees, sir. Not 90 degree. Please don't confuse. Here it is given voltage and induced EMF you check. But previously voltage and current. Sorry, induced EMF and current. But here supply voltage and induced EMF. What the angle between these two? This is not 90 degrees. This is 180 degrees. Understand, students? It is not 90 degrees. It is 180 degrees. It is a square wave. If voltage source is given, input and output waveform is same. But the angle between E and V is not 90 degrees, students. It is a 180 degree. Yes, clear, friends? Is it okay? Yes, Naveen Kumar. Option B is correct. Yes, it's not 90 degree. With respect to induced EMF, you tell. With respect to induced EMF, you tell, sir. Don't confuse. Don't confuse. Yes, friends. Understand? Any doubt? Any doubt here, sir? Clear? I think all of you clear. Yeah. Yes, friends. Can anybody answer this one? Fraction of minute you can answer. If the transformer is excited with a triangular voltage source, then the shape of the induced EMF. Then the shape of the induced EMF. Fraction of minute, students. Fraction of minute. Triangular voltage source. Then input and output waveforms are same. Input and output waveforms are same. It is if the transformer is excited with a triangular voltage source. If voltage source excitation directly you take. The current excitation for given waveform you differentiate one time. That is the output waveform. That is the output waveform. Yes, students. Very good. Very good. Very good. Devika, Sudhir. Very good, students. Come on, come on. Yes, students. It's a triangular. Yes, students. A single phase 50 Hz transformer has the primary number of turns is 100 and secondary number of turns of 200 with a mutual flux of minus 0.05 into T square minus 2T. Find the EMF induced in the secondary winding. Find the induced EMF in the secondary winding, students. Can anybody answer? It's very simple. Find the induced EMF in the secondary winding. This model is important for ESE point of view. Yes, E equal to, yes friends, minus N2 into d pi by dt. d pi by dt. Yes friends, how many number of turns is given at secondary? Secondary number of turns is 200. d by dt of, yes friends, this is d by dt of, what it is given, students? Come on. Minus 0.05 into t square minus 2t. Yes, students. To differentiate this one, this is 200 into 0.05 into differentiation, what you can get? 2t minus 2. Take the 2 is common. This is 20 into t minus 1. 20 into t minus 1, students. Which option is correct? Option B is correct. Very good. Very good. Option B is correct. Minus n2 into d pi by dt. It's very simple. That we can get 20 into t minus 1. If there is no any dot notation like that, it is not mentioned, students. Dot notation, it is not mentioned. But simply, you can apply these formulas. E2 equal to minus n2 into d pi by dt. E1 equal to minus n1 into d pi by dt. If dot polarity like this, it is not given. If dot polarity is given, according to that dot polarity, you take this sign, positive or negative. That is important. Yes, students. Yeah, that is according to Lenz's law, students. Ramesh, that is according to Lenz's law. That is given by both direction and magnitude that I consider. Direction and magnitude. Direction is given by Lenz law. That negative sign. What that negative sign indicates means, according to Lenz law, always induced EMF opposes the rate of change of flux. That is, response opposes the cause. Who is the cause for production of induced EMF? Rate of change of flux. That's why induced EMF always opposes the rate of change of flux. That is according to Lenz law. That is given negative sign. Yes. Come on, friends. Then for this, what is the answer? For a specified input voltage and frequency. For a specified input voltage and frequency, students, if the equivalent radius of the core of a transformer is reduced by half, core of the radius transformer is reduced by half, the factor by which the number of turns in the primary should change to maintain the same no load current. Then how to answer this question, students? Come on. Given that no load current is constant. If the no load current is constant, what about the flux? Flux is also constant. You take the flux is constant. Yes, friends, flux equal to constant. Then you know that flux equal to mmf by reluctance. mmf is, I am writing n into I mu. That is number of turns into current. This is L by mu A. Then what the flux equal to, students? N into I mu into mu A by L. This is the flux. But given that flux is constant, no load current is constant means flux is constant. This I am writing, you know this equation, EMF equation, 4.44 F pi, yes friends, 4.44 F pi N. This is the EMF equation of transformer. Now I am replacing this one, students. Yes, come on, students. What is the EMF equation? This E equal to 4.44 F pi, but pi equal to what you written? Pi equal to what you got, students? N into I mu into mu A by L into N. But assume that we know that transformer is operated E by F equal to constant operation. That's why I am taking this one. E by F equal to 4.44. Yes, students. This is N square into A. Yes, friends. I mu into mu by L. But this 4.44 is constant. This I mu into mu by L is also constant. But assume that we are operating the transformer at V by F equal. Always V by F equal to constant operation is preferable to maintain the constant flux. V by F equal to constant operation is preferable. Then what is N square A equal to, students? Constant. But I want to relate this formula in terms of the radius. Let us assume that A equal to pi r square. Assume that it is a square shaped cone. Then A equal to pi r square, students. Then A is proportional to r square. That you know that n square is proportional to 1 by A. Then what is, students? N square is inversely proportional to A. Then how to write this one, students? Then A you can write. How you can write? N square A equal to constant, students. Then how to relate this one? Then N is square. This N square is proportional to 1 by R square. That is N is proportional to 1 by R. Shall you write like this? N2 by N1 equal to R1 by R2. Then yes, radius is becomes how much, students? Radius is by which the number of turns can change. Half, reduced to half. Radius is reduced to half. That is R1 by 2. Then how many number of turns we can get, students? Then turns becomes N2 by N1 equal to, that is 2N1. The number of turns becomes 2 times. Yes. Yeah, this is the answer. This is the proof. Whatever you told by statement, Sudhir, whatever you told by statement, yeah, that I am giving the proof. That I am giving the proof. But here we are talk Arvind Reddy. Here it is given that reduction of the radius is talking about the radius. That's why you are taking the a square shaped, sorry, not the square shaped. That we are taking the circle core. You take the circle core because he is talking about the radius. He is talking about the radius. It is not given length and breadth. It is not given length and breadth. Arvind Reddy. It is not given length and breadth data, but it is given that it's talking about which one? Radius. That's why you taken that one. The shape is the circle shape. Circle shape. Yes, Amit, good evening. Good evening. Welcome to the session. Yes, Avinash Kumar, still it is not planned. Yes. Yes. Arvind Reddy is okay. Yes. Sudhir. Yes. Avinash, still it is not started. If it is there, then the notification will come. Please subscribe that channel. Please subscribe the channel. Yes. Yes, students. It's a circular core. Yeah. One more question, students. Come on. Can anybody answer this question? The voltage applied to the primary winding of an unloaded single phase transformer is given by. Yes, come on, students. Previous one. What is the answer? Which option is correct? Previous one. Which option is correct, students? Then it is becomes 2 times. It becomes how many times, students? It becomes the 2 times. Is it correct? Yes, yes. Yes, Arvind Reddy. Former it is a grade up. Now it is the BYJU'S. Now it is the BYJU'S. Yes. Come on, students. Can anybody answer this one? Yes. Yes, students. The voltage applied to the primary winding of an unloaded single phase transformer is given by V equal to 800 cos omega t plus 200 cos 3 omega t. The primary has 250 turns and frequency of the fundamental component of the applied voltage is 50 Hz. What is the maximum value of the flux in milliwebers? What is the maximum value of flux in milliwebers, students? Yes, friends, we know that assume that there is no drop. This V equal to E equal to, there is no any drop. Then how you can write N into d pi by dt? You take if you want only magnitude, students, then you take only positive. If you want S, then you take negative sign, minus N into d pi by dt. Then what is V equal to, students? Minus N into d pi by dt. Then I want the flux. Flux equal to minus 1 by N into integral V dt. Flux equal to minus 1 by N into integral V dt, students. Then how to write the formula for flux? Pi equal to minus 1 by N is how much? 250 tons. Yes, friends. Come on. Integration of. Yes, friends. V is how much? 800 cos omega t. 800 cos omega t plus 200 cos 3 omega t. Plus 200 cos 3 omega t. Yes, friends. Now we can write. You can make integration, students. How much you can get? Then what the pi equal to? Minus 1 by 250. Integration you are doing. Then cos omega t. That is sin omega t by, that is 800 cos omega t. That is sin 800 by omega, students. 800 by omega, because it is integration. We are doing with respect to, this is 200 by 3 omega. Sin 3 omega t. Sin 3 omega t, students. Then what you can get? Flux equal to minus 1 by 250 into omega. Take omega is common. Then 800 sin omega t plus 200 sin 3 omega t. 200 sin 3 omega t, students. That is 200 by 3. Come on. This is sine 3 omega t. Can anybody answer how much you got? You tell the flux in terms of milliweber. For F pi equal to pi max, I want maximum flux at omega t equal to 90 degrees. Substitute. In this case, omega t equal 90 degrees only, it becomes maximum. Then pi equal to minus 1 by 250 into omega. 800 into 1 minus 200 by 3. Sin 270 is minus 1. Can anybody tell how much we can get? Yes, students. How much we can get? Come on, students. Come on. Minus 1 by 250 into omega 2 pi f. 2 pi into 50 Hz frequency. This is 800 minus 200 by 3. How much flux we can get, students? Yes, come on. Can anybody answer? This I am getting how much, students? Do the calculation. Come on. Yes, yes. You take only magnitude. If you want to take only magnitude, that is, I am asking pi max this one. This is the pi max. Because at 90 degrees we are getting the maximum value of flux. But I want only magnitude. Because magnitude only it is given in the... Yes, friends. How much we can get? I think you simplify this one. We can get 9.3 milliweber. Is it correct, students? All of you got this one. 9.3 milliwebers. Very good, Amit. I think all of you got this one, students. 9.3 milliwebers. Yes, very good, Amit. Very good. Which option is correct, students? Which option is correct? Then option A is correct. Option A is correct. Very good. Yes, 9.3 milliwebers we can get, sir. One more question is displaying on the screen. Come on, students. An iron core transformer is working at maximum flux density of 0.8 Weber per meter square, students. This is 0.8 Weber per meter square. Is replaced by silicon steel core working at a maximum flux density of 1.2 Weber per meter square. If the total flux remains same, what is the reduction in volume expressed as a percentage of the original volume? The frequency and voltage per turn are the same in both the cases. The frequency and voltage per turn are the same in both the cases. Friends, actually the core is manufactured with 0.8 Weber per meter square. The core material with the flux density. Now it is replaced by high flux density material. I think all of you know this concept. If the transformer core is made with high grade material, high grade means high flux density material, then what is the size of the core is reduced. Then the question is asked, how much volume of the core will be reduced because of this high flux density material? That is the question is asked. How much volume of the core is reduced, students? It's very simple. Come on, students. E equal to 4.44 Bm. Yes, students. F into Bm into ANN. This is the EMF equation of transformer. This is given that E by N. E by N is constant. 4.44 F Bm AN, students. What it is given? EMF per turn is constant. This is constant. This is mentioned in the problem. And frequency is also constant. It is also given in the problem. If it is frequency constant, EMF per turn is also constant. 4.44 already constant. Then which is the constant, students? Bm into AN is constant. Bm into AN is constant. If Bm into AN is constant, Bm is proportional to 1 by AN, students. Then from this, what you can write the formula? Come on. Yes, students. Very important model. Then you can write AN2 by AN1. AN2 by AN1 equal to BM1 by BM2. What is the BM1? 0.8. What is the BM2? 1.2. Is it correct, friends? BM1 is 0.8. BM2 is 1.2. Then how much we can get, students? This is equal to 8 by 12. 8 by 12 means how much we can get? Come on. Yes, students. This is 2 by 3. 2 by 3. But you want to find percentage reduction in the volume of the core. Percentage reduction in volume of the core. Reduction in volume of the core. Yes, friends. Percentage reduction in the volume of the core. Then what you can write? V2 minus V1 by, yes, friends. This is the percentage reduction in the volume of the core, student. Percentage reduction in the volume of the core. You want to write like this? Yes. V1 minus V2 by V1 into 100. This is equal to 1 minus V2 by V1 into 100. But you know that volume is proportional to area. That means V2 by V1 equal to AN2 by AN1. That I am substituting here, students. 1 minus AN2 by AN1 into 100. Directly you can substitute, but for explanation purpose I am writing the some steps. What is the AN2 by AN1, students? 2 by 3 into 100. Then how much we can get? Can anybody? 33.33% we can get. This is the percentage reduction in volume of the core. Very good students. Option B is correct. Very good. Naveen Kumar, Amit Das. Yes, all of you. Percentage reduction is, yes, very good. 33.33%. Very good, students. All of you got this. Option B is correct. The name is Mac D. Souja. Yes. Very good. That is correct. Yes, friends. Here one more question is displaying here. It's very simple question. Come on. Fraction of minute we can answer. Fraction of minute we can answer. Yes, students. Students, please all of you like the session and share the session. Who are the aspirants for GATE, ESE and PSUs? It is more useful. Please share the session and like the session, students. Come on, students, come on. Two transformers and A and B have identical ratings are to be designed with flux densities of 1.2 Tesla and 1.4 Tesla respectively. The weight of transformer A per kVA would be, what is the weight of the transformer? Come on, students, what is the weight of the transformer? Transformer A flux density. Transformer A is designed with a flux density of 1.2 Tesla. Transformer B is designed with a flux density of 1.4 Tesla. The flux density of transformer B, the flux density of transformer B is greater than the flux density of transformer A. We know that, yes, students, flux density equal to pi by A. If the flux density is increases, the area of the cross-sectional area is reduces. That's the reason why the size of the transformer B, the size of the transformer B is less than the size of the transformer A. That means as per kVA, the weight of transformer A, the weight of the transformer A is more than weight of the transformer B. Very good. Option B is correct, friends. Is more than weight of the transformer B. Very good. Next. It's also simple question. This type of models is important for ESE point of. Here I am covering the questions by combining both GATE and ESE point of view, students. Yes. Devika, previous one is, answer is, because transformer A is flux density is less. That's why transformer A size is more. That is weight is more as compared to transformer B. As compared to transformer B. That's why more than that of transformer B. Actually here weight you are defining. Sir, you are telling that size, what about the weight? But kVA rating is same. That's friends. kVA rating is same here. That's why I am comparing directly size and it is the directly it's the weight. Yes, friends. Can anybody answer this one? For understanding the behavior of a transformer, the following laws may be called for. We can use the Lenz's law. We never use Newton's law. We can use Faraday's law of electromagnetic induction. We can use mutual induction. We never use Fleming's right hand rule in transformer. We can use right hand grip rule. Yes, friends, thumb rule, right hand thumb rule we can use to find the direction of the flux. Right hand thumb rule we can use to find the direction of the flux. That's why 1, 3, 4, 6. Which option is correct? Option D is correct. 1, 3, 4, 6, students. We never use Fleming's right hand rule. We never use Fleming's right hand rule in transformer. Fleming's right hand rule is used to find the direction of dynamically induced EMF. But in transformer, which EMF, students? Statically induced EMF. In a transformer, which EMF, students? Statically induced EMF. That's why we don't use this Fleming's right hand rule in transformer. That's why which rules we can apply? 1, 3, 4, 6. You know that what is the transformer principle? The transformer works on the principle of mutual induction. Students, in the option, if the mutual induction is not there, then you can select Faraday's law. If Faraday's law and mutual induction is given in the option, what the principle of transformer? Your answer is mutual induction. If mutual induction is not there, then only go for Faraday's law of electromagnetic induction. Yes, students. Clear? Come on, students. Yes. Yeah. These are not the options. This one important concept, students. Please concentrate. One important concept. The instantaneous polarity of the primary winding of an ideal transformer is shown in figure. The polarity of instantaneous voltage is the secondary. Students, here it is not talking about load is connected like that. It is not talking about like this. It is asking according to polarity of primary, what is the polarity of secondary? Not with respect to load. Not with respect to load. It is asking what is the polarity of secondary with respect to polarity of the primary. Come on, students. In every circuit that I am going to explain here. Actually, here the plus is given, here minus is given. That's why I am taking this is entering current and this is the leaving current. Now, what is the direction of current? This is plus, this is minus. That's why I am taking this is the dot. Okay, then no need of dot here, plus minus. According to plus minus, you can tell. This is the direction of current, students. Okay, this is the direction of the current. Come on, student. This is the direction of the current. Then apply right hand thumb rule. The curved fingers indicate the current direction. Thumb indicate the flux direction. Thumb indicate the flux direction. Come on, students. Now see the flux direction here. What is the flux direction? This is the direction of the flux. Okay, this is the direction of the flux. That is, this is the direction of the flux, students. Upward direction. That means in this winding, come on, students. In this winding, not for transformer action. It is not asking for transformer action. For transformer action, primary flux and secondary flux must be opposing. That you know. But here it is not asking for transformer action, just a coupled circuit. According to plus minus of primary, what the secondary polarity it is asking, students? It is asking. That's why. Come on, students. Now, here I want flux direction is like this. In the secondary winding, apply the right hand thumb rule. The flux direction is like this. Then current must be like this. Current must be like this. Then current must be like this means this is the direction of the current. This is the direction of the current, student. Current is like this only. Then see the sense of winding. Current is going inward. Again it is coming outward. That's why this is the direction of the current. Come on, students. Because to satisfy this direction of flux, this is the direction of the current. Now, current is starting here. That's why this is the plus. This is minus. That's why what the polarity? Minus plus. Come on, students. Here not according to transformer action. For transformer action, two fluxes must be opposed. But here we are not talking about secondary flux. We are talking about only primary flux. Only primary flux. According to primary flux only we are talking. Yes, friends. The flux is in secondary winding. Flux is downward direction. Apply right hand thumb rule. Current must be flowing like this. Then compulsory start here. Then only current will start. Will go like this. First inward, again come to outward. That's why current is started here now. That's why it is a plus. That's why it is a plus, students. And this is the minus. That's why C is negative, D is positive. Yes, students. Come on. Next. Can anybody tell what the direction of, what the polarity of induced EMF in this one? Yes, same. Because plus is given here. That's why I'm taking current direction here. Yes. What the direction of current? This one. See this one, sense of winding also you concentrate. Sense of this current is flowing on inward direction, it coming out. Understand, students? Now what is the direction of the flux? What is the direction of the flux, students? Come on. What is the direction of the flux? This is, apply the right hand thumb rule. This is the direction of the flux. The direction of the flux is like this. Come on, students. Come on, this is the direction of the flux. Now this is the direction of the flux. Then according to this flux direction, this is the current direction. See the sense of winding. The sense of winding is started here. But here the sense of winding is started here. That's why this is the current direction. Yes, then only the current will flow like this. Then only the current will flow like this. Then we can satisfy the flux direction. Then we can satisfy the flux direction. Then current is started here now. This is plus, this is minus. Very good, very good. Yes, friends. Similarly, now you tell me. Yes, friends. Here the plus is given. The current is like this. See, the current is like this. Wherever the plus is given, from that point I take in the current direction, entering. But this is inward entering, outward coming. Like this. This is the direction of the current. See the sense of winding. See the sense of winding, students. See the sense of winding. That is important. Now this is the direction of the current. This is the direction of the current. Then what the flux direction? Apply right hand thumb rule. Downward direction. This is the direction of the flux. Come on, students. This is the direction of the flux. Okay. Now, yes. Here flux direction is like this. Outward. Flux direction is outward means the current direction must be like this. Current direction apply. To satisfy this flux direction in the secondary winding, the current direction must be like this. Yes, friends. Current direction must be like this. Then to make that the current direction is, yes, friends, where it will start? Yes. The current direction must be like this. Then it start here. It comes to inward. Then we can get, see the current direction. Sense of winding is important. It starts here, then goes outward, inward to outward. Yes, friends. This is plus, this is minus. C plus, D minus. Then this we can check this one, students. You check this one. Yes, this is the current direction. Yes, this is the current direction. Yes, now it is okay, students. Now okay. Is it okay now? Still any problem? Okay, students. Yes, please go through this one. Yes, friends. If it is not visible here, I'm writing once again. I think all are understand this one. I'm writing once again, students. I'm writing once again. If it is not visible. Yes, I calculated VB. Now I want to calculate VC. I want to calculate VC, students. Then how to calculate VC? You apply like this. VA by VC equal to VA by VC equal to, yes, students, NA by NC. NA by NC. Then from this, what is the VC you can calculate? VC equal to how much, students? NC by NA into VA. Then how much VC we can get? You substitute here 60 by 200 into 100. This is how much we can get, students. VC equal to how much we can get? 30 volts we can get. Is it okay? Now what is VXY? This VXY is VB minus VC, students. What is VXY? Is the VB minus VC. Come on, students. VB minus VC. This VB minus VC, that equal to 50 minus 20. 50 minus 30. How much we can get? 20 volts. All of you got this one, students? All of you got? Just I am applying the turns ratio with respect to each winding. Just I am applying the turns ratio with respect to primary to each winding. Primary to each winding. Primary to each winding. I am getting the 20 volts, students. Clear? Please once again go through this very important model. Very important model, student. Any doubt? Any doubt, student? Yes. Come on, come on. This is, yeah. One more important model of question. Come on, students. The relative current direction through primary and secondary of a single phase transformer connected to a resistive load on second. It is a transformer action. We want to fulfill the transformer action here. Side indicate in the various cross-sectional views given in figure. Which of these are correct representations? Students, one point to remember. To satisfy transformer action, very important. To satisfy transformer action, that is, two fluxes must be opposing. Two fluxes, that is primary flux and secondary flux. Primary and second, or HV flux and LV flux. Primary and secondary fluxes must be opposing. Primary and secondary fluxes must be opposed. That is called, then only transformer action is possible. Because transformer is a negatively coupled circuit. Transformer is a negatively coupled circuit. Very good, Devika. Previous one is 20 volts. Yes. Transformer is a negatively coupled circuit. That's why primary and secondary fluxes must be opposing. To satisfy transformer action, students, to satisfy transformer action, there is a two conditions, students. There is a two conditions. Here I want to write. Just a minute. Yes. To satisfy transformer action, if the two windings are placed on the same limb, if the two windings, yes friends, if the two windings placed on the same limb, placed on the same limb, yes friends, this I am giving with respect to satisfy the transformer action. If you have any confusion here, this sentence I will write in the next slide. This sentence I will write in the next slide. No problem. Just a minute, sir. Don't feel. Just a minute. Yeah. This I am writing to satisfy transformer action. If the two windings placed on the same limb, it must carry the current in opposite direction. It must carry that concept, you know. It must carry the current in opposite direction. In opposite direction. It must carry the current in opposite direction. If the two limbs placed on, if the two windings placed on the two separate limbs, if the two windings placed on separate limbs, come on students, separate limbs, it must carry the current in same direction. It must carry the current in same direction. Carry the current in same direction. These conditions must be satisfied. Why these conditions, students? To satisfy transformer action. To satisfy transformer action. What do you mean by transformer action satisfaction? Satisfaction, students. That is, two fluxes must be opposing. Two fluxes must be opposing. To make two fluxes are opposing, this type of current direction is required. Two fluxes must be opposing. Two fluxes. must be opposing. That is the primary flux and secondary flux must be opposing. Then in this case, yes friends, come on, see the first one. These windings are placed on the separate limbs. It must carry the current in the same direction. Here current is entering. Here also current is entering. That's why it is satisfying. It is satisfy the transformer action. Yes friends, it satisfies the transformer action means two fluxes must be opposing. Two fluxes must be opposing, friends. For example, apply the right hand thumb rule at primary side. Flux, this is the direction of the current. This is the direction of the current. Then flux is like this. Let this is the primary flux. Then apply here also, students. Here also current is entering. Flux is like this. Flux is like this. Let this is the secondary flux. These two are opposing. These two are opposing. That is transformer action is satisfied. Two fluxes are opposing. Next. See this one. If the two windings are placed on the same limb, primary winding and secondary winding is placed on the same limb. It is carrying the current in opposite direction. It is carrying the current in opposite direction means this is also correct. If you want, check this one. Apply right hand thumb rule here, friends. This current is leaving. Current is leaving. This is the direction of the flux. This is the primary flux. Current is entering. This is the direction of the flux. Secondary flux. Then primary flux and secondary flux is opposing or aiding, students. Opposing. That's why it is also satisfy the transformer action. It is also satisfy the transformer action. Yes, friends. See the C. Yes. Apply this one. Two windings are placed on the same limb. But if the two windings are placed on the same limb, it must carry the current in opposite direction. But it is carrying the current in the same direction. This is wrong. If you want, check this one. Yes, current is leaving. This is the direction of the flux. This is the primary flux. Here also current is leaving. This is the secondary flux. The primary flux and secondary flux is aiding. Primary flux and secondary flux is aiding. This is wrong. It is not satisfy the transformer action. Yes, if the two windings are placed on the separate limb, it must carry the current in opposite direction. Sorry. Yes, friends, it must carry the current in the, if the two windings are placed on the same limb, it must carry the current in opposite direction. But it is carrying if different limbs it is placed, it must carry in the same direction. But this is opposite direction. If you want to apply this one, students, current is leaving. This is the direction of the flux. This is the direction of the flux. Yes, current is entering. This is the direction of the flux. This is the direction of the flux. This is pi s. This is pi p is also same direction. This is the wrong. Two fluxes must be opposed. Then only transformer action is possible. Then A is correct, B is correct, students. Not AD, sir. A and B is the correct. Not AD. A and B is the correct. Simply you remember, students, no need to check these flux directions, all these. If the two windings are placed on the same limb, it must carry the current in the opposite direction. It must carry the current in the opposite direction, friend. It must carry the current in the opposite direction. This is satisfying because dot cross cross dot satisfied. If the two windings are placed on the separate limb, it must carry the current in the same direction. Cross cross dot dot satisfied. That's why it is correct. But it is dot, it is also dot. That's why it is wrong. It is dot, it is cross. This is cross, this is because separate limbs. It is also wrong. That's why A and B is the correct. A and B is the correct. Not A and D, sir. It's A and B is the correct. Please concentrate. Clear, friends? Is it okay? Friends, a 400 volts for 200 volts 50 Hz 3-winding transformer. Come on, students. It's the 3-winding transformer. Is connected as shown in figure. The reading of the voltmeter. It's very simple, very simple. Let us assume that based on the dot I am giving the polarity. This is plus minus. This is plus minus. And this is the plus minus. Apply KVL in this loop. Apply KVL in this loop, friends. If you apply KVL here, what you can get? Minus plus. This is how much it is given? 200 volts. It is how much? 200 volts. It is how much? 400 volts. Minus plus. This is 200 plus 200 plus minus 400. This is equal to 0 volts we can get. The reading of the voltmeter equal to 0 volts. Very good, Devika. Previous one is AB. Yes, friends. Yeah, 0 volts. Just we can apply. According to dot polarity, I am giving the plus minus plus minus. Here the dot. That's why plus minus. Then apply KVL. Minus 200 minus 200. Aiding polarity. But plus 400. Minus 200 minus 200 minus 400 plus 400. That equal to 0 you can get. Yes, very good students. Yes, come on students. Yes. In single phase core type transformer, LV and HV windings are arranged as. How we can make the LV and HV winding, students? This type of winding is more preferable. Yes, this is called interleaved winding or concentrated winding. This is called interleaved winding or concentrated winding we can use. Why interleaved winding or concentrated winding is preferable? To reduce the leakage flux. To reduce the leakage flux. And always LV is placed nearer to the core. You have so many advantages are there. If LV is nearer to the core, HV is outside. That's why we are placing LV insulation. This is LV insulation. LV insulation. Next what you can place, students? LV winding. Next we can place the LV winding. First LV insulation, next LV winding. Okay, clearly I am drawing, just a minute. This type of procedure is preferable. It is called interleaved winding or concentrated winding. On each limb you follow like this. On each limb. Why interleaved winding or concentrated winding is preferable? To reduce the leakage flux. First I am placing the LV insulation. This is LV insulation. Next LV winding. Next which one, students? LV winding. LV winding. Next HV insulation. Come on students. Next HV insulation. This is HV insulation. Next HV winding. This type of winding procedure is preferable. This is HV winding. HV winding. I want to change the color. Okay. This is the HV winding. Yes, friends. This is LV insulation, LV winding, HV winding. This side also. LV insulation. Yes, friends. LV insulation. Next, LV winding. Next, HV insulation. Next, HV winding. This is called interleaved or concentrated winding. On each limb you can place like this, friends. This is which one? LV insulation. LV winding. HV insulation. HV winding. This procedure you follow. That's why, but always LV winding is nearer to the core. LV winding is nearer to the core, students. This is the cross. Then this is the dot. Then this is the dot. This is the dot means this is the cross. Understand, students? LV and HV winding sections. Half of HV is near the core and half of LV is outside the HV. Yes, outside the HV on the each limb. Half of LV is near the core and half of HV is outside the LV on each limb. Which option is correct, friends? Which option is correct? Very good. Option D is correct. Half of LV is near the and half of HV outside the LV on each limb. Then this type of winding is called interleaved or concentrated winding, students. Yes. Come on, students. Yeah, this I am giving assignment for you. So please check this one. Assignment. Just apply the E equal to N into d pi by dt formula. N into d pi by dt formula, students. We can get the answer. This is 800 by pi volts we can get. We check that one, students. For time being, I am giving assignment. As what the conservator tank purpose? What the purpose of the conservator tank? Yeah, that you know. Please go through this one, students. Yes. Yeah, this is the function that I given. The function of the conservator tank is that I explained. Please go through these points. Please go through this point. What the function of oil in a transformer? Mainly oil in a transformer is used for insulation purpose, cooling purpose and also for protection purpose. Protection purpose. Buckholes relay is operated if in a transformer oil, that is in oil type, that is the transformer must be consist of oil. In oil type transformers only Buckholes relay is operated. In that oil is referred for protection also. Insulation, cooling and protection. But here protection is not given. Mainly you select the insulation and cooling. In detail about the transformer oil also I given some points, students. For transformer oil I given some points. Please go through these points. Yes, students, this is about today's session. Tomorrow I am going to solving the important models of questions based on the EMF equation. Very important models that I will bring. Please don't miss that class, students. Tomorrow I am going to solving the very important models of questions based on the EMF equation. Yes, students, this is my Telegram channel. Who are not joined still now, you please join this channel for more updates about my lectures. And if you have any doubts, clarification, you please share your doubts, friends. This is our BYJU'S exam preparation. Get it on Google Play, students. Thank you very much. This is about today's session, students. Thank you very much. Yes, students, please go through this who are not attended. And tomorrow I am solving the very important models of questions based on the EMF equation of transformer. Day after tomorrow, operation of transformer. This will continue, students, up to this month ending. The total different models of questions on the transformers that I am going to solve. Yes, students, thank you very much. Amit, thank you. Yes, Ratwa, thank you. Yes, Amit, whatever the doubt you asked in network theory, I will send today. Yes, because of some work, I am not responding. Okay, I will send in my Telegram channel. Amit, I will respond. Yes, tomorrow also same timing. Tomorrow also same timing. Naveen Kumar. In YouTube is same timing. If any timings are changes, then I will inform in my Telegram channel. I will share in my Telegram channel if any timings are changes. Yes, Sai Kumar, Naveen Kumar, Amit Das, all of you who are attended this class, all of you, thank you very much, students. Thank you. Ramesh, yes, all of you, thank you very much, students. Naveen Kumar, yes. I'm ending the session, students. Thank you.